Hi, this is Mike Lawless, and in this video I'm going to discuss dataset curation and A&E classification model building using ADMET Predictor 8. For this example, I'm going to use a recent Chemical Information and Modeling set. So this is the publication, and then we're trying to develop a model for hERG blockers. So this is a 2016 article, fairly recent article. So the first thing I'm going to do is read the molecules in and curate the data, their training set. The first thing I'm going to do is find duplicates, and there's two different options here. The first one is ignore chirality, so I'm going to get exact duplicates, and then in the second step I'm going to look at the duplicates where the chirality of a particular molecule or bond is different between the two molecules. Then I'm going to perform a match molecular pair analysis on the data set, and I think find some interesting trends. I hope you agree. And then finally take a subset of the data set and build an artificial neural network ensemble classification model. So I'll first open up a SMILES file containing the non-blockers. So this is the data set of their training set. First it's the non-blockers. So double click on that. And the SMILES string is provided in the second column and the ID the first column. So the program goes and tries to find the SMILES column, and this time it's identified it as the second column. So just go ahead and click OK. It's brought up a message saying there are 5 warnings recorded, so let's take a look at those. So in this first molecule there's an odd valence of iodine atom, and then the second ones we've got silicon, mercury, two molecules with mercury, and then one with selenium, and these just aren't parameterized. So I'm just going to look at the AP warnings. If you click on it once, it sorts in ascending order. Click on it twice, descending order. And I'm just going to take all these compounds and delete them. I'm not sure about this. Obviously, the program will handle iodide, but this is an odd valence. And then these other compounds contain heavy metals that the program is not parameterized. So I'll just go up to Edit and go down to delete. So it deletes those 5 molecules. Now let's just highlight all these molecules, and I can do that by clicking on the first compound and then just scrolling all the way to the bottom and selecting the last one. And then I'm going to go up to Data, Add Compound Attributes. So these were all of the non-blockers. I'm going to select constant value from the dialog box. I'm going to use textual data. The field name will be called hERG blocker. And these are the experimental nodes. So these from the publication should have an IC50 of greater than 10 micromolar for all these compounds. So just click No. It's added this column as the nodes here. And the next thing I'm going to do is import the structures for the training set blockers. So just double click on that. It's in the same format. So click OK. I'm not going to skip any compounds with duplicate names. I'm just going to read all the data in, and you see down here that it's read 282 compounds in from that data set, and we've got a total of about 700 compounds. Now, since these are already selected, I'm going to go ahead and go Data, Add Compound Attributes, and only take the selected compounds and add a constant value. This time, instead of the attribute value being yes, or excuse me, no, I'm going to change it to yes. So I click on that, and now it's added yes field for all of these compounds. And we can look at the distribution up here with the distribution plot. Specify the hERG blockers. I only want 2 bins, and then click OK. So there's about roughly 400 non-blockers and about 280, as we just saw, blockers. Okay, now I'm going to clean up some of the columns here and undisplay them. So if I go to the SMILES string, I can just right click on that and say undisplay column. Similarly, I'm going to undisplay the AP column, keep that column, and then the rest of the columns I'm going to go up to View, Arrange Columns, and I'm just going to select those and push them over to the left. In other words, remove them. So now we have a column with just hERG blockers, and I'm going to color these according to a heat map. So I'll select hERG blocker, use the red, yellow, green, and then click OK. Then if I sort this column, you see that all the no's are in red. Now, usually red means stop, and since these are negatives, I'm going to change the direction so that if it's a non-hERG blocker, it's green, and then if it's a hERG blocker, it's red. Now I'm going to standardize the functional groups here. So I go into chemistry, standardize functional groups, and then click OK. Okay, so there were none that were standardized, so this is in the form that we like for AdMet Predictor. Next, I'm going to go in and neutralize these molecules. So I click OK, and it goes through and it neutralizes some of the compounds. So if I sort this again in descending order for the structure, and make this just a little bit wider here, maybe bring this over, and then make all of the rows a little bigger. So I hold down the control key and then move this up and down, and it resizes all the rows according to that. So you can see when they created their data set, they used protonated groups here, and we just want non-protonated in AdMet Predictor, so we'll just go ahead and neutralize those compounds. So that looks good there. Okay, so now we can use the program to find duplicates. I'm going to again hide this column or undisplay it. So in order to find duplicates, I just go up to Data, Find Duplicates, and that'll bring up this dialog box. You can either look at duplicate structures or any attribute in the any text attribute in the data set. Here I'm going to leave all these as default for this one, and then place the duplicates next to each other in the spreadsheet. So click OK, and then you can see it has 10 compounds selected. Now, some of those might be triplicates, so we kind of have to eyeball these a bit. I'm going to go ahead and scroll down to the last duplicate, which is this set, and then take all of the rest of them and hide them. You can either go up to the View, Hide, unhide, and I'm going to hide the selected ones. So now we only have the duplicate molecules showing up here. And if we look at this first duplicate, we see that the structures are the same, but you'll notice that the hERG activity value is different for these. So we can't use these in a model. I guess you could, and the positive thing would be is that you'd get half of them correct. The negative is you'd get one of these wrong, so you get one or two. Also, I think it's going to confuse the algorithm to look at two compounds that are identical descriptors, but in two different classes. So we're going to need to rectify that and remove those. One way we can get a better visual on this is to decrease the size quite a bit so that we can see all these on the screen. And the pairs are going to be under one another. So we've got the first two we're going to have to get rid of. The next two are duplicates, but the data is different, so we need to remove those. And if we just look down, we've got all just duplicates, no triplicates. So I can select this one and then kind of eyeball going down, 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 and it looks like these first several pairs are all compounds that we're going to have to remove. So I'll highlight them and then just hit the delete key. And then let's look at a few more of these. So these two compounds are the same and they're in the same class, so we only have to delete one of those. I'll select the second one and delete that. Now another pair here we need to delete, and then this pair here, same structures but different results, and that's going to confuse our model building, so we need to remove those. And then finally we have one that are identical, so I'm going to select this second molecule and delete that. So now we've got all the compounds that are exact matches, and we've rectified those. So now I'm going to go up here and view everything. So view, hide, unhide all. So now we have 662 molecules, and this time I'm going to look for duplicates, and I'm going to ignore chirality this time. So again, I click OK. It's selected 13, and so I'll go down here again to this last pair here and then highlight everything below there. and then we're just going to unhide this. Now, one command I use a lot, or keyboard shortcut, is just Control Alt Hide, and as you can see from this menu here, hide, that will hide what's selected. So there's nothing selected now, so that's why it's grayed out. Okay, so let's again go to the top here and again shrink the rows up so that we can get all of these kind of on the screen at once. So again, you see a couple of duplicates here going down further. And let's see, I think there's a triplicate in here, so that would be these compounds. So right in here we have 3 compounds that are identical except for that chirality. Remember, that's what we're matching here. Now, the reason we need to rectify these is because AdMet Predictor uses just 2D descriptors, so the descriptors aren't going to differentiate between these 2 molecules. Let's look at the first pair here. And so we're going to have to, because these are in different experimental classes, just delete those 2. And then similarly, the next pair, this pair here, also the data disagrees, so I'm going to delete those. And then if you look at this set of chiral compounds, if you had the hydrogen here going back, it's a blocker. If it's coming forward, it's a blocker. But then where it's undefined, it defines it as not a blocker. So again, I'm going to delete all 3 of those because they're inconsistent. This pair, we only need to delete 1 out of the 2 because we have the same value of the experimental value. For these compounds, these differ. Let's get rid of those 2. Similarly for the next pair, and then also this pair here. And then so we're on a roll. So if we look at these 2 compounds, they differ due to bond chirality around the double bond. Again, we're not going to be able to differentiate that, so we'll just delete those 2. These 2 look fine. Both chiral forms have the same result, so we'll only delete 1 of those. Similar for that pair, and then this pair, they disagree, so we'll have to delete those. So now we've got all those rectified. I'm going to again unhide all, and let's go ahead and save this as an intermediate file this time, and I'm going to save it as an XTK file in the same directory, and I'm just going to call this training, let's see, hERG training data. So now the next thing I want to do is look at match molecular pairs. So I can either click on this tab down here that says pairs, and it'll define all, bring up a dialog box. I can also go into the chemistry and say generate pairs or activity cliffs. So I'll click OK here. We're going to leave all of these to the defaults, and then we're going to go down for the hERG blockers and set that to 1. So if it finds any pairs that meet these criteria, it also has to identify compounds where the value is different. One's a blocker and one's not a blocker. So I just click OK, and that's very quick. Now it's generated these pairs, and this says go to the pairs tab if you want to see the pairs that were generated. So I'll click on that, and then let's resize these rows so you can see them a little bit better. And I'm also going to resize these columns in here. So this first column here is the hERG activity of the structure 1 columns. This is the hERG activity of the structure 2 columns, and I'm just going to move these over just a little bit, and then this is the difference over in this field. So if we look at these first 2 molecules, you just see that the plus charge has gone from this atom over here to this atom over here. So essentially these are structural tautomers. They give different results, so that would be a pair of compounds that we would need to delete from the data set. Now, so that we delete that one. Now what this is telling us is that for these 2 very similar compounds, the one with the OH in this position as compared to a hydrogen in this position is not a hERG blocker, but if you don't have that OH, it's considered a hERG blocker. Now that might be difficult for the model to differentiate those two molecules, but on the other side, let's assume this is real data, and this is a good data point. For this next compound, adding the compound with a methyl group here is not active, whereas if you remove that, it's active. Now, if we look at these two compounds here, I think I know this one on the right. This is actually caffeine. And so in the data set, it says that the IC50 of caffeine for the hERG channel is under 10 micromolar, so it's considered a hERG blocker. Again, the model might have some difficulty. This is kind of the opposite trend here. Here you removed a methyl group and it made it a non-blocker. Here you're adding a methyl group and it made it a non-blocker. So those compounds you might want to look at once you've created the model and see how those come out. Okay, again, here we've added a methyl group here, becomes a hERG blocker. Methyl group here becomes a hERG blocker. Adding a bromine to this compound on the right. Now this is going to affect the lipophilicity of the compound, so maybe more lipophilic compounds are hydrogen, or excuse me, hERG channel blockers. So that's another thing you can kind of keep in the back of your mind. If we go down a little further, this is an interesting one. So we have a carboxylic acid on the left-hand side and then just a methyl group on the right. So potentially adding acidic groups inactivates the hERG activity. So this compound, you see this nitrogen would be protonatable. If you've got the acid, it's going to be a zwitterion. Similarly for the next pair, so this molecule is the same, but an OH here made it a hERG blocker. And then if we look at the final, or another, and then this final one, we've added this whole group out here, and it becomes a hERG blocker. So that's our data set. Let's go back to the compounds tab, and we've got 640 compounds here. And what I did was just take a random set of about 150 of these, and I'm going to use that to create our hERG model. Now to show the model building capabilities within ADMET Predictor 8, I've read in the example file of just 150 random compounds from the data set that we just curated. We have our hERG blocker, non-blocker column, and then I've calculated all the descriptors and the ADMET properties for this series of molecules. So I could select ADMET Modeler from this icon here, or I can go up to Tools and click on ADMET Modeler. Also a Shift M as a shortcut will bring up this. So the first thing it asked me to specify is the dependent variable. So I'll click on the hERG blocker, then click OK, and we get the dialog box for ADMET Modeler. So this is the first dialog box that comes up. You do have a choice here of changing your dependent variable if you wanted to. You could also logify it, and then you could scramble it. And scrambling is useful for scrambling the data to make sure that you're not getting a random correlation. Random seed gets set, and we could give it a different random seed, or if you like a certain lucky number, you could click it, put it in there. We have all of our descriptors on the right by default. If we want to add something like log P or log D, some of these models, we could also add that at this time. Additionally, if you calculated your own descriptors, they would appear on this left side, and then you could just pull them over to the right, and they'd be available for creating a model. So now just click on the next. We get the next dialog box. Here's where we can define our test set. I'm going to leave the default to a Cajonas map and find about 10% of the compounds here. Next, I'll go into the descriptor sensitivity set, and I'm going to select input gradient. This is a fairly small data set of 150 compounds, so input gradient should perform fairly quickly. I'm going to click OK, and then click the next button. Here's where we specify the grid for the artificial neural networks. We can just click autofill, and it gives us a reasonable size grid. I'm going to go from 1 neuron to 5 neurons with a step of 2, and then go from 5 to 15 descriptors with a step of 2, and then leave everything else as default. go to the summary. Here's where you can kind of look at how you've set things up, and if you don't like it, you can go back to the previous and change. I'm just going to click build. It specifies me what is the negative class, which is the ones with the no in them, and then it begins building models. Now by default in ABAP Predictor 8, it's showing the Uden values for these particular compounds, or excuse me, for these models, and you can see that all of them look very nicely, and then it's color coded the best model in green. So this has picked up this model, as you can see. So if we click on that with the left mouse button click, it'll bring up the performance grid. You can see you can turn off the training set to see how we did on the test set, and so this molecule is not predicted to be a hERG blocker, but experimentally we have it as a yes. We can also turn on the training set and just look at these statistics and maybe interrogate some of these molecules down here. This one looks like it might be a reasonable hERG blocker, so I'm not sure why that was incorrectly predicted, or the observed value. So let's go ahead and close that. Now the model performance grid you can set different parameters there, and for example it's considering model complexity. Let's turn that off and see what kind of results it gives. So now it's picked this one kind of down in the lower left hand corner. Maybe this is a better model. It looks like it's got fewer incorrect predictions. We're still only going up to 15 inputs, which I don't think is that bad. Now the only thing is it's kind of at the edge of where we were, of our data sets, or excuse me, our parameters. Maybe we want to rerun this and go with 7 neurons to see how that would go, and then maybe out to 17 just to see if you add a couple more descriptors, if that vastly improves the model. You can look at sensitivity, which is quite good for this model. Specificity seems excellent. So this looks like a pretty good model. If we want to save the model, we would right click on it and export the model, and then you can have your choices to save the model. We'll call it a hERG model 1, let's say, and then the only other thing is we want to change the tool set. Maybe we want to say hERG model built on 150 compounds. Click save. Now that's going to be in our list of models now. So if we next thing we'd want to do is save the project if we want to come back to this. So we'll call it hERG model _001, and then click save. And then now we need to specify where to save that data set. So I'll save it right into this and select the folder. So that's saved in there. If I want to go back and bring this up again, I can. Just going to close this, exit. Now when I come back, it says, would you like to recalculate the ABMAP properties? I'm going to say yes, because we've got a new model, and then just click calculate to calculate all the data. And then we could go into our user models, and now it's defined this as the hERG model. Let's bring in some more data, or the original data, by arranging the columns and then going down here and selecting our experimental data, which was called hERG blocker, added over here. So now this is going to appear in this, and it's color coded. Let's go ahead and color code the model values in the same fashion. Again, we want to reverse both these directions. So only for this one, descending, I must add that set. So if we sort on hERG blocker here, and then do a secondary sort here, we'll see all the true negatives. And then as we start scrolling down, so we got most of these right. So here's some compounds where we predicted a yes and it was no. So these are your false positives. We got a couple of false negatives, so we predicted no's here, but the experimental value was yes. And then the rest of these are all going to be yes. So that looks like a reasonable model. Now you might want to apply these to an arbitrary set of compounds, maybe compounds you're looking at in lead optimization. Thanks for watching this video. I'm Mike Lawless, and if you have any questions, please contact me at Simulations Plus. You can either call this phone number listed here or send me an email at mlawless@simulationsplus.com. Thanks again for watching, and we'll see you next time.